Latent heat. Consider a body of liquid water at 100 degrees Celsius. We must continue to supply heat to that liquid water to convert it into water vapor. But the temperature doesn't increase during this process, so where is the heat being hidden? Another way of saying hidden is latent. So the heat that we have to provide to change the phase at a constant temperature is referred to as the latent heat. Before we move on to discuss what latent heat is, we need to define something known as specific enthalpy, which is the enthalpy per unit mass of a system. Lowercase h is equal to uppercase H divided through by m, the mass of the system. Remember that enthalpy is a measure of the total energy of a system, including the internal energy U, and the amount of energy required to make room for it by displacing its environment and establishing its volume and pressure, and that's PV. So lowercase h is equal to U plus PV all over m. Latent heat quantifies the amount of hidden heat that must be supplied to change the phase of a substance. And the extra heat must be supplied to change the phase of the substance at constant temperature because the specific enthalpies of the different phases are not the same. And in general what we have is that the specific enthalpy of the vapor is greater than that for the liquid, which is greater than that for the solid. So why is that the case? Well, we need to think about the equation for enthalpy, and it's written here, lowercase h is U plus PV on m. And if we consider the liquid to vapor transition, and here we have a blue line indicative of an interface between the two, the volume of the vapor is very much greater than the volume of the liquid. And so the vapor has to do more against the environment to establish its own pressure and volume. So the specific enthalpy of the vapor will be greater than that of the liquid. What about the solid to liquid transition? Well, if we consider an unbounded molecule to have zero energy, the more strongly bounded that molecule is, the more negative its potential energy. And that's what's indicated in that schematic there, that the potential energy for a solid is more negative than that for a liquid. The internal energy contains information about the potential energy. So we have to provide that energy to change the potential energy to more loosely bind the molecules as they are in a liquid compared to that of a solid. So the enthalpy of the liquid compared to the vapor is smaller, and the solid compared to the liquid is also smaller. So we'll define then latent heat as the difference in the specific enthalpies of two phases of a substance at the same temperature. So if we let subscripts I and j label two different phases of a substance, then we'll have symbolically that Lij is equal to Hj minus Hi. So for example, written below, we see that the latent heat of vaporization, that is moving from the liquid to the vapor phase, is equal to the specific enthalpy of the vapor minus the specific enthalpy of the liquid. And that will be positive, and that will be the energy that we have to provide to ensure that we can change phase. At 0 degrees Celsius, water has the following latent heats. So they're weakly a function of temperature, but at 0 degrees, liquid to vapor is about 2.5 by 10 to the 6 joules per kilogram. For solid to liquid, it's 0.33 by 10 to the 6 joules per kilogram, and solid to vapor, it's 2.83 by 10 to the 6 joules per kilogram. And if you add the liquid to vapor to the solid to liquid, then you get the solid to vapor transition.